Let's investigate the principle of duality. So in set theory, we've seen that we can combine sets together with set operators, and we have a notion of equality of sets. So let E be a set theory equation, which will just be an equation consisting of sets and operations on sets, and perhaps some equality of different set expressions. We can then form the dual equation of E by replacing each occurrence of the union operator, the intersection operator, any reference to the universal set or the null set in the original equation E by the intersection operator, the union operator, the null set, or the universal set respectively. So what this is saying to us is, if we have a set theory equation, we can then look at forming a new equation by replacing the union operator with the intersection operator, replacing any instances of the intersection operator with the union operator, replace any reference to the universal set with the null set, and replace any reference of the null set in the original equation with the universal set. So we take an original equation, apply these rules, these transformation rules. Union operator goes to intersection operator goes to union operator, a reference to the universal set will become a reference to the null set, and a reference to the null set will become a reference to the universal set. If we take these actions, the resulting set theory equation will also be true. Let's have a look at some examples. Okay, we've 4 examples given here. We start off with an initial set theory equation in the column E, and we're going to transform that to a new set theory equation using the principle of duality. So for the first one, we have A union B equals B union A. Let's apply the rules according to the principle of duality and get a new equation. So the union operator will be replaced with the intersection operator. So in this case, the dual of the initial equation E will be A intersection B equals B intersection A. The second example we have is A intersection A equals A. Again, applying the principle of duality, we will replace that intersection operator in the initial equation with a union operator in the resultant equation, the dual of E. In this case, we will have A union A equals A. And these are both true expressions, statements, equations. The third example then is A union A complement, and this is the universal set. Applying the rules according to the principle of duality, we replace the union operator with the intersection operator, and we also need to replace the reference to the universal set with a reference to the null set. The resultant equation in this case is A intersection A complement is the null set. And finally, the last equation we have is A intersection B intersection C. The parentheses here indicate that we should do the B intersection C operation first, take the resultant set, and then form the intersection with set A. So A intersection B intersection C equals A intersection B intersection C. The resultant equation, applying the principle of duality, would be A union B union C equals A union B union C. And these equations will hold true. So if equation E is true, after applying the principle of duality, the dual of equation E will also be true. The final topic we will consider in this lesson is the topic of power sets. The idea with a power set is we want to actually determine all of the subsets of a given set. So if we're given any finite set A, by finite we mean it has a set of elements where we can actually count them up to a certain point. So it's not an infinite set. We have a set of elements with a distinct number n as the number of elements in the set. So given any finite set A, we can ask the following questions. What are all the subsets of the set A? And how many subsets of the set A are there? So to answer these questions, we introduce the set of all subsets of the given set A, and this is called a power set of A, denoted by P of A. Let's have a look at an example. So if we're given the set A equals 1, 2, and 3, what we want to do is essentially find all of the subsets of the set A. Well, we know that the null set is a subset of every set, so that's going to be in the list. Also, we can then extract from the initial set all of the other subsets. So we end up with a list containing the null set, the set with the element 1, the set with the element 2, the set with the element 3, the set with the elements 1 and 2, the set with the elements 1 and 3, the set with the elements 2 and 3, and finally, every set is a subset of itself. So we finally end with the set with elements 1, 2, and 3. So the thing to note here is that the power set, the elements of the power set are sets. So there's nothing wrong with a set having its elements being other sets. And if we count the number of elements in the power set in this case, we will see that we have 8 elements. Okay, so the cardinality of the power set in this case, the power set of A, is 8. In general, for any set S, the number of elements in the power set of S is 2 raised to the power of the number of elements in S. Okay, and we can represent that by the following equation. The cardinality of the power set of S equals 2 to the power of the cardinality of the set S. Okay, so let's take an example. The set of all students in the BSHC 1A Introduction to Mathematics for Computing class. Let's say that there are 65 students registered in this class. We can then calculate the number of subsets, 2 raised to the power of 65. And you can see that this is an extraordinarily large number. So even with 65 students, the actual number of subsets that we can generate from that initial set ranges into the billions and zillions. Okay, so in summary, in this lesson we have looked at Venn diagrams, how we can actually represent relationships between sets in a diagrammatic or pictorial fashion. We looked at the principle of duality, which gives us the capability of transforming one set theory equation into another set theory equation. And we've ended with the idea of power sets. Okay, with a power set, we're trying to look at all of the subsets of a given set. Let's look at some examples. Okay, let's look at the principle of duality. We will create a set theory equation, and then we'll actually apply the theory behind the principle of duality to that equation. So let me commence then. Principle of duality. Let's take as an example a universal set containing the elements 1, 2, and 3. And let's also take some subsets of this universal set. Set A containing the element 1, and set B containing the elements 2 and 3. Okay, so to represent this in a Venn diagram, we would represent the universal set, again, by a rectangle. We have the set A with the element 1, and we've got the set B containing the elements 2 and 3. Okay, and these are disjoint sets. There's no overlap between them. They don't share any common elements. So we can see from the diagram that A and B, if we take the union of A and B, it will represent the universal set. So that will result in the set theory equation. The universal set, in this case, equals A union B. Okay, so let's apply the principle of duality to this equation. And the resultant equation will also be true. So we know that the universal set, any reference made to the universal set in the initial equation, we want to replace that with a reference to the null set. We also want to look at the operators involved, and the union operator will be replaced with the intersection operator. So the final equation, applying the principle of duality, will be the null set equals the intersection of A and B. And we can see that from the diagram. And scroll up again. So having a look at our Venn diagram, we can see that the sets A and B are disjoint. And remember, disjoint sets, their intersection is the null set. Let's finally end with an example regarding power sets. So here we're trying to determine all of the subsets of a given set. So let's take, for example, the set A, containing the elements A, B, and C. Well, first of all, what are the subsets of this set? Let me list them out. Okay, I'll start with the first subset in the list. A1 is going to be the null set. A2 is going to be the set with a single element A. A3 is going to be the set with a single element B. A4 is going to be the set with a single element C. A5 is going to be the set with elements A and B. A6 will be the set with elements A and C. A7 will be the set with elements B and C. And finally, A8 is going to be the set A itself, elements A, B, and C. So the power set of A, represented by P of A, is going to be the set of all subsets. So it's essentially going to be the set containing elements A1, A2, A3, A4, A5, A6, A7, finally A8. So the elements of the power set are sets themselves. That's key. The number of elements in the power set, you can see, is 8. So the cardinality of the power set in this case is 8. And we can see that just by counting these elements in the set. If we want to write out the power set in a longer fashion, we can again just list the elements. So the first one, A1, was the null set. A2, set with element A. A3, set with element B. A4, set with element C. A5, set with elements A and B. A6, the set with elements A and C. A7, the set with element B and C. And finally A8, set with elements A, B, and C.